Welcome to my second lecture in this series on tensors. This indeed is my second series on tensors. In the first one, we had focused primarily on tensors under linear coordinate transformations, whereas in this series I am focusing on tensors under general coordinate transformations. Now let me quickly recapitulate what we talked about in the previous lecture. Under a coordinate transformation where x1, x2, x3 up to xd goes over to x prime, which is a general function of x, a smooth invertible function, then the coordinate differentials dx primes transform in a linear fashion. Dx prime mu turns out to be del x prime mu del x nu times dx nu. This is nothing but the standard formula for the total differential in partial differential calculus. Here, of course, we are assuming the Einstein summation convention that an index which is repeated upstairs and downstairs as a superfix and a suffix is to be summed over. Notice that the new coordinate differentials, that is the coordinate differentials of new coordinates, are linear combinations of the older coordinate differentials with coefficients given by these partial derivatives. And one major difference between this and the case of linear coordinate transformation is the following. For a linear coordinate transformation, these same coefficients would have just been constants, same at all places. If you had x prime mu equals lambda mu nu x nu, then these del x prime mu del x nu's for the linear coordinate transformation would have simply been lambda mu nu. Same no matter what x's you are talking about. However, for a general coordinate transformation, the coordinate differentials do combine linearly, but the coefficients that go into the linear combination depends on the point in space or space-time, whatever you are using at that point. Now, the important point is we can use this transformation to define transformations of other physically important objects. A scalar, for example, is something which will not change under a coordinate transformation at all. So if you start with a scalar phi, it will just become phi prime, which is the same as phi. On the other hand, vectors transform exactly like coordinates, or rather, they used to transform like coordinates under linear coordinate transformations. They still transform linearly, but under general coordinate transformations, they transform like coordinate differentials. So, a vector is a d-component object a1, a2 up to ad, which transforms under coordinate transformation to a prime mu is del x prime mu del x nu a nu, still a linear combination of the old components or of the components in the old coordinate system, with del x prime mu del x nu the same coefficients as the coordinate differentials. These coefficients are called vector transformation coefficients. Here what you do is differentiate the newer coordinate with respect to the older one. On the other hand, covectors are another kind of d-component objects which are written with a lower index, b prime lower mu, and the transformation rule is again a linear combination of the older components b nu's, but now the components are given by del x nu del x prime mu, derivatives of the old coordinates with respect to the newer ones. Now, an immediate consequence of this kind of transformation rule is that if you form a mu b mu, a upper mu b lower mu, a contraction, something that we are going to look at in some detail soon, between a vector and a covector, the resulting thing actually turns out to be a scalar. In fact, the reason why we postulated this as a transformation law for covectors is that we wanted to describe objects which, acting linearly on vectors, would give us scalars. Now, by combining the rules for vectors and covector transformations, we can go on to higher order transformation rules, like if we stick to second rank, tensors come in various kinds. the 2, 0 tensors transform like the product of two vector components, a mu, b mu. Of course, this means a total of d square components, mu taking d values and mu also taking d values. And the way this product transforms under a coordinate transformation tells us how any 2, 0 tensor, which will have two indices mu and nu, transforms. T prime mu nu will be del x prime mu, del x lambda, del x prime nu, del x sigma, t lambda sigma. Note once again here that these two coefficients here are vector transformation coefficients, and you multiply them together to find the transformation coefficient for a 2, 0 tensor. Let me stress once again, the new components of a 2, 0 tensor are again linear combinations of the old components. The coefficients happen to be products of two vector transformation coefficients. Now you can have 1, 1 tensors which are like products of a vector and a covector, a upper mu, b lower nu, and this can immediately tell us the t prime mu nu, the transformation rule will be del x prime mu, del x lambda, vector transformation coefficient, times del x sigma, del x prime nu, t lambda sigma. And finally, a 0, 2 tensor transforms like the product, the outer product of two covectors. T prime lower mu nu is del x lambda, del x prime mu, times del x sigma, del x prime nu, t lambda sigma. In all these cases, the new tensor components are linear combinations of the old tensor components, the coefficients being products of appropriate number of vector or covector transformation coefficients. And the transformation coefficient that you have will of course depend on whether you have an upstairs index or a downstairs index. An upstairs index corresponds to a vector transformation coefficient. A downstairs index corresponds to a covector transformation coefficient. And this can be generalized to any order. Just to make sure that we understand the general situation, I am talking of a rank 5 tensor. I could have chosen a larger one or a smaller one, is just for illustration, where you have 3 upstairs indices mu, nu and rho, and 2 downstairs indices in the middle somewhere, lambda and sigma. Now each of these 3 upstairs indices mu, nu and rho will correspond to 3 vector transformation coefficients. They are all going to be multiplied together to form a single coefficient. So del x prime mu, del x a, del x prime nu, del x b and del x prime rho, del x e, whereas lambda sigma in the middle will correspond to downstairs indices version, that is covector transformation coefficients, del x c, del x prime lambda, del x d, del x prime sigma. And when you multiply all these coefficients together, you get the single coefficient which multiplies t, a, b, c, d, e. Of course, here on the right hand side you have actually d to the power 5 terms which are being summed together. A, B, C, D and E are dummy indices which each take d values each, and this whole equation is a single equation, but it actually stands for d to the 5 different equations, because mu, nu, lambda, sigma, rho, the free indices in this expression, can take a total of d to the 5 different values, each of the indices being capable of taking d different values. Now, a very important point is that vectors and covectors are really nothing but tensors. They are tensors of rank 1, 0 and 0, 1 respectively, which is why a vector has a single vector transformation coefficient, and a covector, being a 0, 1 tensor, has a single covector transformation coefficient, rather trivially. What is perhaps a bit more non-trivial to say is that tensors are also vectors, in the sense that if you take the set of p, q tensors at a particular point and linearly combine them together, you do get another p, q tensor. The set of all p, q tensors at a given point form a linear vector space. Now, the problem is, if you take tensors at different points and try to compare them, then you run into trouble, simply because adding or subtracting tensors at different points will not give you a tensorial object, simply because when you transform your coordinates, tensors at different points, even tensors of the same rank at two different points, will transform with different coefficients. So the difference will not really give you something meaningful. Now, why is that an issue? It's an issue because one of the most common things that we do in mathematical physics is differentiate objects. And if you want to differentiate, say, a tensor with respect to position or time, as the case may be, when your coordinates involve space-time, you will have to subtract neighboring values of the tensor. And that will not in general give rise to a tensorial object. How to handle this issue will occupy us for the latter half of today's lecture. Before beginning today's lecture in earnest, let us take a quick detour into a particular example. This is a familiar example to most of you, and this will help you understand clearly exactly what we are doing when we are transforming coordinates. So, the example that I have in mind is a very well-known one. It's a transformation in 2D space from the Cartesian to the polar coordinate system. So, our original coordinates x1 and x2 are nothing other than x and y, our familiar Cartesian coordinates, whereas x prime 1 and x prime 2 are nothing but polar coordinates r and theta respectively. As you all know, x and y are related to r and theta by this simple set of relations. X is r cosine theta, whereas y is equal to r sine theta, and the inverse rules will give you r and theta in terms of x and y. In fact, these are what you would perhaps call the direct rules. x1 x2 to x1 prime x2 prime transformation is given by r equals square root of x square plus y square and theta equals tan inverse y by x. Now, using these, it's pretty easy to figure out what the derivatives are, and these derivatives, remember, are what are going to sit in front of vector and covector transformations. When we are talking about covector transformations, you will have to differentiate the old coordinates with respect to the new ones. So del x del r, del x del theta, del y del r and del y del theta are what you need, and it's easy to see that these are what the expressions are. For vector transformation, on the other hand, you need the derivatives of the new coordinates with respect to the old ones, del r del x, del r del y, del theta del x and del theta del y. It's absolutely straightforward to calculate these set of coefficients. Now, under xy going to r theta, how does a vector transform? If you look at a vector's one component in the new coordinate system, in this case, in the polar coordinates, a prime 1 will be given by del x prime 1 del x1 a1 plus del x prime 1 del x2 a2. And that del x prime 1 del x1 is nothing but del r del x. And this derivative here is del r del y. And just by substituting the values that we had just now seen, we get a prime 1 is x over square root of x square plus y square into a1 plus y over square root of x square plus y square into a2. So a prime 1, which is a prime r, once you replace a1, a2 by ax, ay and so on, and just use the expressions for x and y in terms of polar coordinates for simplifying this, we get a prime r is cosine theta ax plus sine theta ay. This should actually ring a bell to those of you who know how to handle polar coordinates, which of course would be most of you. Now what about a prime 2? A prime 2 is going to be del x prime 2 del x1 a1 plus del x prime 2 del x2 a2. And this one of course is del theta del x, this is del theta del y, and substituting the values we get minus y over x square plus y square a1 plus x over x square plus y square a2. So a prime theta, which is what a prime 2 is actually something which simplifies to minus sine theta over r ax plus cosine theta over r ay. At this stage, those of you who are familiar with polar coordinates will actually have seen something rather strange and disturbing. It seems that there is a mismatch between what we already know about polar components of a vector and what we have just now figured out. Well, just to recap, this is basically how you set up basis vectors in the polar coordinates. The standard basis vectors that you study about in, say, first year in college. So, if you have a point P here with coordinates r and theta with respect to some origin and some choice of initial direction, this angle being theta and this distance being r, the unit vector in the radial direction er is simply the unit vector in the direction in which r increases, whereas E theta is the unit vector in the direction in which theta increases. These of course do not match the Ex and Ey unit vectors, which are our familiar I and j, unit vectors in the direction of increasing x and y. And it's easy to see from this diagram that Er makes an angle theta with Ex and 90 degree minus theta with Ey. So Er is obviously cosine theta Ex plus sine theta Ey. It takes a slightly more thought to figure out that E theta is minus sine theta Ex plus cosine theta Ey. So Ar, the radial component of a vector, can be easily figured out from this expression. It works out with cosine theta Ax plus sine theta Ay, whereas A theta, the cross radial component, the polar coordinate, is minus sine theta Ax plus cos theta Ay. Note that we had written down A prime r, A prime theta with superfixes. Here we have used suffixes, but that has really nothing to do with covector versus vector. Both sets actually denote components of a vector. I am just using suffixes here to distinguish between what we had calculated a while ago, A prime upper r and A prime upper theta, with what standard polar coordinate transformations would tell you. Notice that while AR and A prime r are the same, A theta and A prime theta are not. And what we are going to do now is explore the reason behind this mismatch. Of course, the relationships that we have is A prime r is exactly the same as AR, whereas A prime theta is actually 1 over r times A theta. And the reason for this mismatch is pretty simple. It's all in the basis. Notice that when we use standard polar coordinates, the kind we learned in, say, the first year in college, or maybe even high school, we are using unit vectors. Er and E theta are both vectors of unit length. However, in our study of tensors so far, we have not mentioned anything about length. And indeed, in a more general setting, defining length is something we have to do by invoking additional structure. We cannot even talk about the length of a vector with whatever tools we have developed so far. So when we talk about the basis vector corresponding to r and the one corresponding to theta, the ones we have used when deriving these new components A prime r and A prime theta, we actually have no way of saying beforehand that they are going to be unit vectors. The length of the vector simply doesn't make sense at this stage. What we can definitely say, however, is that they are vectors corresponding to unit change in the coordinate. Of course, if you were to change r by 1 unit while keeping theta fixed, you would be moving in a straight line. On the other hand, changing theta by 1 unit would actually involve moving in a circular arc which is not straight at all. To keep track of the fact that vectors are essentially linear objects and don't curve, we essentially talk about infinitesimally small vectors and infinitesimally small displacements. So when you talk of the xy coordinate system, the basis vectors that are used simply describe changes of delta x and delta y respectively. Delta x, when you're talking of the vector along x, increasing x, where y is held fixed, so delta y is 0 for one of them, and delta y is a displacement change in y for the other vector that we use, the other basis vector that we use, and we involve no change in x for that. Now, one of the easiest ways of seeing what will happen when you carry out such a displacement is simply to take a look at a function f of x and y and ask how much will that function change. If you are looking for a change of x and x alone through delta x, a function f of xy changes to f of x plus delta x comma y. What is the change here? The change is the difference between this, and that, at least for a small delta x, is given by del f del x into delta x. And we have already seen before that we cannot really talk about very large changes, especially when we are using other coordinates, because the curves will then no longer be straight lines. We only talk about infinitesimal changes. So delta x has to be infinitesimal, and we would like to talk about the rate at which f changes when you just change x. So here we can see that as you move along the x-axis, that is, as you move by changing x and x alone without changing y, a function f changes by the amount del x acting on f per unit delta x. Similarly, when you change y and y alone, f of x comma y changes to f of x comma y plus delta y, a change per unit delta y of del y acting on f. Keep this in mind. Now let's look at the polar coordinate situation. Here, the basis vectors that are used, not the unit vectors er and e theta. Once again, unit vectors are things we cannot really talk about at this stage. The basis vectors describe changes in delta r without changing theta, and change in theta without changing r, respectively. So, if we are only moving r, a function f, now I am writing this as f tilde simply because even if we want to keep it numerically equal to f of x comma y, once we have changed the arguments, the functional form definitely changes. So let's talk of any general function f tilde of r and theta. When you move along r, that is, you just change r and not change theta by an amount delta r, f tilde r theta changes to f tilde r plus delta r comma theta. Exactly similarly, a change of del r acting on f tilde per unit delta r, and for delta theta, for which this change per unit delta theta is extremely important. Remember, the curve that you get when you change theta and theta alone is not really straight unless you use an infinitesimally small delta theta. There the change is del theta of f tilde per unit delta theta. And it's this change which we actually want to encapsulate in the notion of a basis vector. In the basis vector that we use in the xy system, you can actually call them I and j, but in advanced differential geometry, they are actually denoted by del x and del y. The fact that they look like partial derivatives come as a surprise, but it should not really be a surprise. You should realize that all you are saying is that these are how you measure the rate at which a function f changes as you move along increasing x or increasing y. Of course, this is just notation at this stage, and del x and del y are nothing but I and j. The basis vectors in the r theta system are denoted by del r and del theta respectively. But notice that when you actually change through unit r, per unit change in r, you actually move unit distance along the radial direction. So del r and er are actually the same. Whereas when you change through delta theta and keeping r fixed, you are actually moving in a circle of radius r through an angular shift of delta theta. So the actual amount you move is not really delta theta, it's r times delta theta. So displacement which is in the direction of e theta is actually r times delta theta e theta. Per unit delta theta you get r e theta. That's what del theta actually stands for. So the identification is pretty straightforward. In the xy coordinate system, the basis vectors that you use, despite this perhaps unfamiliar notation of del x and del y, are nothing but I and j. In the r theta situation, the basis vectors that you are using actually are not er and e theta, they are er and r times e theta respectively. This difference is simply because when you change theta, you move the point not by delta theta but by r times delta theta. Now notice that if I use a prime r and a prime theta as my components and del r and del theta as the basis vectors, this is what our overall vector should be. A prime r times del r plus a prime theta times del theta. Notice that a prime r we have already seen is ar, the radial component that we usually have seen. Del r is the same as er. A prime theta on the other hand, the one we had calculated, is actually 1 over r times the standard cross radial component a theta. But the basis vector del theta is actually r times e theta. These two factors of r cancel and you actually have ar er plus a theta e theta. So there is really no inconsistency. The fact that transforming to polar coordinates give you a polar component or a theta component of a vector which does not match what you learned of as cross radial component of a vector is simply because the two basis vectors that we are using are different. With these examples out of the way, let us begin today's lecture in earnest. One important thing that we should stress is that the definition that we have given of tensors as d to the power r objects, r being p plus q, which transform in a particular manner under coordinate transformations, actually is not perhaps its best definition. A much better and easier definition to understand could be the following. A tensor is nothing but a multilinear map. For example, the 0 to tensor that we are talking about here we talked about that as a bunch of d square numbers which transform in a particular manner when you do a coordinate transformation. A much better way to talk about them would be something which maps two vectors to a scalar. That is, instead of the t mu nu components, we can think of t, the object, which acts on two vectors a and b and produces a number. That number is t mu nu a mu b nu. Now what we need to make sure is that the definition that we have given is compatible with this one. That is, assuming the tensor components really do transform the way we say it, this quantity t mu nu a mu b nu is going to really be a scalar. Checking that out will not be very difficult. We will write t prime mu nu a prime mu b prime nu. Here I have used green for the tensors, the blue here for one of the vectors, black for the other vector. Now t prime mu nu is simply the term in green on the right hand side. Del x a, del x prime mu, del x b, del x prime nu, t a b. Let me stress once again, it's pretty easy to remember. You are going to just use the fact that these two are downstairs indices, so you will get covector transformation coefficients with the new coordinate downstairs in the derivative. A and B are dummy indices. You could use anything you want. All you need to do is make sure that you are not confusing them by accidentally putting in the same dummy index in different places. So A prime mu, for example, for that I have to use a vector transformation coefficient, del x prime mu, del x c, AC, that's A prime mu. Note that I have used the dummy index c here just to ensure that I am not going to confuse this with A or B. And finally, b prime mu is del x prime nu del x d bd. Now, note that here this partial derivative and this partial derivative, they are different kinds of partial derivatives. This is a co-vector transformation coefficient, this one is a vector transformation coefficient. But they share the same index mu. One's upstairs, another downstairs, so there's a sum involved. Now let's bring such terms together. So these two terms we are bringing together, and this one I am bringing together with this one, where again there is a sum over the mu index which is repeated. Now this combination is simply del xa del xc according to the way in which total differentials are done. And this combination is nothing but del xb del xd. So we replace these two products and sums of products actually by these two coefficients. And now notice that xa's are of course independent. So if you were to differentiate xa with respect to xc, you are going to get a 0 unless a and c are equal and 1 if they are equal. So this is really delta ac and this one is delta bd. So now our sum has become much simpler. AC and BD have delta symbols attached to them, which means that unless A and C are equal, you are going to get a 0. Unless B and D are equal, you are going to get a 0. So if you carry out the sum over C and D, you are simply going to get TAB, AA, because the only value of C for which you get a non-zero value is C equal to A times BB. And this exactly is what you started out with. TAB, AA, BB, of course you could write this as T mu nu, A mu, B nu as well. This is exactly the same as what you get after the transformation. So under a coordinate transformation, this quantity T mu nu, A mu, B nu, which T maps A and B to, is a scalar. So this tensor as a multilinear map which maps two vectors to a scalar, that's borne out by this calculation. You can easily check. For example, this tensorial object T prime mu nu lambda sigma rho would actually stand for a tensor which takes in 5 arguments, the first 2 of which are covectors, the second 2 are vectors, and third one is a covector again, and maps them all multilinearly into a scalar. That is to say, if you take T prime mu nu A lambda sigma rho, multiply that by A lower mu, B lower nu, C upper lambda, D upper sigma, E lower rho, 3 covectors and 2 vectors, you are going to end up with a scalar. If you want some practice, you should actually check explicitly that this thing really gives you a scalar by carrying out the same kind of calculation that we have done right now. Notice that as we have seen earlier, for the expression like A upper mu, B lower mu, or here for an expression like T lower mu nu, A upper mu, B upper nu, indices which are contracted over, same index repeated and summed over, tend to cancel each other out. That of course is because of the fact that on their own an upstairs index and a downstairs index leads to opposite transformations, and that's where the cancellation comes from. So summing up over contra and covariant indices tends to cancel the transformation. In this case, what we have seen is you had one contravariant or vector transformation index, one covariant index, and summing up over these values ended up with a 0 index thing. Similarly, summing up over both mu and nu here led to something without an index, a scalar. Now, this is actually a very important property called contraction, and let me just stress this once again. If you had a tensor, a mixed tensor with one upper index mu and a lower index mu, that of course is d square objects. But if you decided to form T mu mu, which is put mu and nu the same and sum up over all possible values, T11 plus T22 up to TDD, this entity from what we have said right now, should behave like a scalar. And let's check whether that is true. Remember, t prime mu nu is del x prime mu del x a del x b del x prime nu t a b. We just use the same thing except that we use the same value for mu and nu and of course imply the sum. So we get del x prime mu del x a as before, and instead of del x b del x prime nu we get del x b del x prime mu t a b. Now this summed up over all mu is simply del x b del x a, and that's delta b a, and therefore once this summation is done you end up with t a a. So t prime mu mu is the same as t a, which of course can also be written down as t mu mu, something which will not change under a coordinate transformation. So t mu mu is a scalar. Well, you can do something similar for a more complicated scenario. Suppose you have mu nu lambda sigma rho phi for indices of t. 4 upstairs indices, 2 downstairs indices. And instead of mu and sigma being different, we put them equal and added up over all possible values of mu. So, mu, lambda, rho and phi are the only free indices left. The mu is a dummy index, it no longer can be ascribed a particular value. The important thing is, when you carry out a transformation of coordinates, this mu with the upper sign will give you a vector transformation coefficient del x prime mu del x a, and this mu will give you a covector transformation coefficient del x d del x prime mu. And a, b, c, d, etc. have been chosen just to contract it properly with here. But notice that if you take these two terms together, del x prime mu del x a and del x d del x prime mu, and sum up over mu, this is nothing but partial derivative of xd with respect to xa, so delta dA, and therefore you still have these 4 transformation coefficients, 3 vector transformation coefficients corresponding to nu, rho and phi, and 1 covector transformation coefficient corresponding to lambda. But other than that, these 2 coefficients have essentially disappeared, and in the tensor you have T, A, B, C, A, E, F. So the same contraction between the first and the fourth index as you have done here. So essentially if you do a contraction of 2 indices, they just end up disappearing from the transformation root. The next result that we will talk about gives us a nice way of identifying tensors. Suppose you have an expression which looks like this. A mu nu lambda sigma b rho phi is equal to T mu nu lambda sigma rho phi. And in this expression, we already know from some other consideration that A mu nu lambda sigma are components of a 2, 2 tensor, and T mu nu lambda sigma rho phi are components of another tensor, 4, 2 tensor. Now, given an expression like this, where of course all the indices are in their rightful places, we would be forced to conclude, and this is what the quotient rule tells us, that this unknown bunch of numbers b rho phi actually form components of a 2, 0 tensor. Of course, the fact that we have used a 2, 2 tensor and a 4, 2 tensor already here, these are just special cases for the sake of illustration. The general rule should be easy to guess from here. As long as you are forming this kind of products, outer product so to speak, of a tensorial object with an unknown object, and you are getting a tensorial object with the right number of components, with right indices, then the unknown object must also be a tensor. So this is what the quotient rule says, and I am going to quickly try to convince you that that is true. So if you carry out a transformation of coordinates, you know what the new components of A and T are going to be, but you do not ab initio know what the new components of B are going to be. By the way, let me also stress one thing. This rule works provided the statement that AB equals T is correct for arbitrary tensors A and T, not just for very specific tensors. That is one thing that has to be borne in mind. Now, once we know the transformation rules for A and T, we can of course try to use that to figure out how B would transform. Now at this stage we do not know what B prime rho phi is, so we leave that as it is. But for A prime mu nu lambda sigma, I am putting in the correct vector transformation coefficients and co-vector transformation coefficients appropriately as far as the indices are concerned. Similarly, for T prime mu nu lambda sigma, I am also using the appropriate vector and co-vector transformation coefficients. Here, of course, you are going to get a product of 6 such coefficients, 4 vector transformation coefficients and 2 co-vector transformation coefficients. And notice that here we have used A, B, C, D as dummy indices, A, B, C and D. Here we have used I, J, K, L, M, N. That's simply to ensure that we do not mix up 2 different dummy indices in the course of the calculation. So let me stress once again, here we are not using the general relativist standard convention that Latin indices stand for 1, 2, 3 and Greek indices stand for 0, 1, 2, 3. Here all our indices run from 1, 2, 3 all the way up to D or 0 to D minus 1 as the case may be. So now, let's see how we can relate the two things together. Of course, all I have to do here is Tijkl I already know is Aijkl times Bmn. What I want to do is figure out how B prime rho phi is related to Bmn. Of course, that means that I have to get rid of all these coefficients from this side. Now here, we have to be a bit careful. When we want to get rid of these, we essentially have to use the inverse relationships. And that's not really very difficult to come by. After all, we know that del x prime mu del x a, for example, if we were to contract this with another del x prime mu, we say del x alpha, you'll automatically get delta alpha a. So that's straightforward. The only thing you have to worry about is whether you can carry out the contraction at all. That is, whether before you carried out the contraction, this index mu were free. The reason why I am saying that is simple. Here, in this left hand side, mu is a free index, a is not, a is repeated. So you have no right to use another del x a, del x prime something to try to get rid of this del x a. This del x a, in a sense, has already been spoken for by this a index here on capital A. So the only free index you have is this. So what you can do is actually multiply by exactly this function, del x prime mu of x alpha. Once again, I am using Greek indices here to avoid possible confusion, and since the other Greek indices that we have used are from the middle of the Greek alphabet, I am going to go towards the beginning in this case, alpha, beta, gamma, delta and so on. So del x a alpha del x prime mu to get rid of this. Similarly, you want to get rid of this factor, you would want to bring in a del x prime mu, del x beta. When you come to this term, you notice that xc is actually spoken for already. The c is a dummy index. Is the x prime lambda which has a free index here. So for this, you have to multiply this by del x prime lambda of del x gamma. And similarly for this one, you have needed del x prime sigma, del x delta. Of course, you do it on both sides. That is, you multiply by these factors and of course add up over mu, nu, lambda, sigma on both sides. What will happen on the left hand side? This and this together will give you delta alpha A. This and this together will give you delta beta B. This and this is actually del x c, del x gamma, so delta c gamma. And similarly this and this will give you delta D delta. Hopefully you will not confuse this delta, which is an index, with the Kronecker delta. And exactly similar thing will happen on this side. This and this together will give you delta alpha I. This and this will give you delta beta j. Here you get delta k gamma, and here you get delta L delta. Of course, these two coefficients will still survive. They are not being contracted with anything. Now we use the magic of the delta symbol to simplify the sum on both sides. Here, when you sum up over A, all the A's become alpha, all the B's become beta, and so on. So you end up with A alpha beta gamma delta, B prime rho phi, is del x prime rho del xm, del x prime phi del xn, A alpha beta gamma delta into Bmn. Now this has to be true no matter what values the A alpha beta gamma delta, the components of the tensor A takes. Remember, that's what we said. This expression is correct for arbitrary tensors of the right kind. So it stands to reason that the coefficients of A alpha beta gamma delta must match on both sides, and this gives us the transformation rule for B. B prime rho phi has to be del x prime rho del xm, del x prime phi del xn, Bmn, which is exactly the way a 2-0 tensor would transform. Now, as you must have guessed by now, this does not have to be restricted to a 2-0 tensor multiplying a 2-2 tensor or something. As long as the indices match on both sides, the quotient rule can be relied upon. If you have an outer product of a tensorial object and the unknown object, and the result is a tensorial object, the unknown object must be a tensor of the correct kind. Indeed, this also works if there is a contraction involved. If T lower mu, A upper mu nu were equal to B nu, where T and B are known to be 0, 1 and 1, 0 tensors respectively, this would imply that A mu nu would have to be a 2-0 tensor, and so on. Let us now turn to a topic which is of immense importance as far as the application of tensors to physics is concerned, especially in subjects like general relativity. The question is, are derivatives of vector fields or covector fields themselves tensors? In particular, is this quantity, a quantity with two indices mu and nu, given by the partial derivative with respect to x mu of a covector component a nu, a tensor? We use del mu nu as shorthand for this, and of course we need to know how the various pieces transform. How do del x mu transform and how does nu transform when you want to carry out this calculation as to how this del mu nu is going to transform. Now, under a coordinate transformation, if it is a linear transformation, then x mu goes over to x prime mu given by lambda mu nu x nu, and the inverse of this x mu, the original x, is L inverse says mu nuth component x prime nu, where this is the mu nu component of L, and L inverse's mu nu's component is actually L inverse transposes mu nuth element, which according to our notation is lambda mu mu with the opposite placement of the indices. So x mu is lambda nu mu x prime nu. The reason why we are talking about this is simple. First of all, we need to know how del x prime mu is related to the old derivatives, or rather derivatives with respect to the old coordinates. And that's straightforward. You just use the standard chain rule in partial derivatives. Del x prime mu is del x a, del x prime mu, del x a. And for this, we will need these factors. Is lambda mu a, this del x a. On the other hand, if you want the whole transformation, you just get lambda mu a from here, and the coordinate transformation of course leads to a transformation of the covector components. A prime nu is lambda nu b ab. Now remember, the coefficients here are constants. This is the case for linear transformations, where the coefficients are the same at all space points, which means that this coefficient lambda nu b can be pulled out of this derivative, and you get lambda mu a lambda nu b del a ab, which is exactly the transformation rule for a 0 to tensor. So del mu nu is a 0 to tensor under a linear coordinate transformation. What makes this question really interesting is whether the conclusion will survive when we carry out a non-linear transformation, a general coordinate transformation. And that is a more complicated question. Once again, del x mu of a nu under a coordinate transformation becomes del x prime mu of a prime nu, and I'm going to write a prime nu in terms of the older components, the unprimed ones, and that's easy. You just use a covector transformation rule, del x b del x prime nu ab for a prime nu. And because these are functions of the old coordinates, I must change this del x prime mu to a derivative involving old coordinates by using exactly the same argument that we used a while ago. This again is just the chain rule for partial derivatives. But now comes the big difference. Unlike in the case of the linear transformation, this factor is not independent of x's. And what that means is when you carry out this derivative, you cannot just pull out this term. You end up with two terms, one in which this term gets pulled out and the derivative goes and acts on AB, which is what we had for linear transformations as well. But for general coordinate transformations, we have this additional term where del x a goes and acts on B. And in fact, it's easier to actually use the original form del x prime mu for this partial derivative, this whole thing. When that goes and acts on del x b, you get del 2 xb del x prime mu, and of course, ab is not differentiated in this. The presence of this additional piece destroys the tensorial structure. Notice that if we were to claim that del mu a nu were a tensor of whatever kind, then if I knew all the components of del mu a nu in the old coordinate system and I knew the coordinate transformation, that would be enough to find out the new components of del mu a nu in the new coordinate system. But notice that here what we are getting is del prime mu a prime nu is related to del a ab through these coefficients, which is exactly what a tensor transformation rule would tell you. But in addition to that, you also need to know the AB components themselves in order to figure out the transformed version. A tensor has a transformation rule which is A linear and B depends only on the components of the tensor and the transformation of coordinates. You don't need any further information to carry out transformations for tensor components. Here you need to know AB in order to carry out this transformation, which means del mu a nu is not tensorial. You have an additional piece which ruins the tensor property. Now this is of course critical because very often we will need to take partial derivatives of vector fields or covector fields or tensor fields later on, and here we see that doing this will not give us a tensorial object. Remember, the reason why we want tensorial objects is that once we have expressions which involve tensorial objects only, the covariance is something which is manifest. You do not have to actually go and do complicated calculations to check whether the equation is covariant or not. So, if general coordinate transformations is expected to be a symmetry of your theory, and it definitely is for general relativity, you would want to write expressions involving tensors. Of course, you don't really have to, in the sense that even if you use non-tensorial expressions, you may be still able to show the covariance with a lot of calculations. But writing things in terms of tensors makes life a lot easier. Del mu nu not being a tensor is a bit of a dampener in this case. Of course, I forgot to tell you one thing, but this is essentially the same as what I have already told you. The non-tensorial nature of the transformation of del mu nu implies that even if del mu nu had components, all of which vanished in a particular coordinate system, they may not all vanish in another coordinate system, which essentially is the reason why covariance is ruined by a term like that. So if you have an equation like x mu nu equals del mu nu, where x mu nu is known to be a tensor, this may even be correct in some frame, but will not be correct in all coordinates.
The question now is, how do we remedy the situation?
Let us now try to define a different kind of derivative. We will talk about the geometrical meaning of this derivative in great detail in a later lecture, but for the time being, just let us take a look at a definition, one which is designed to get rid of that additional pesky term which was ruining covariance. So the definition is capital D mu nu, my new kind of derivative, is the same as del mu nu apart from this additional correction term. The correction term is proportional to the components A. Of course, it depends on the indices mu and nu. So the kind of expression that you can write down, which is not going to be covariant, but will at least obey my rules for placement of indices properly, is one in which you have a coefficient which has a lambda index upstairs. This lambda is of course a dummy index summed over, and mu both on this capital gamma. The gamma, lambda, mu nu are functions, of course d cube functions at this stage, which are somehow designed to get rid of the non-covariant term in del mu nu. Of course, notice that because we want d mu nu to be covariant and we already know that del mu nu is not, that is, d mu nu is tensorial, del mu nu is not, this term overall cannot be tensorial. So gamma, lambda, mu nu's cannot be tensorial objects, despite having one upstairs index and two downstairs indices. Now, let us try to figure out what kind of transformation rule should we demand on the gamma, lambda, mu nu's to ensure that d mu nu does behave like a tensor. That is, we want d mu nu prime in the new coordinate system to actually be del x prime mu del x of xa times del x prime nu of xb times del dA ab. So this is the transformation rule for 0 to tensor which we want to ensure. Of course, in the new coordinate system, d mu nu prime is nothing but del mu nu's transformed value minus gamma prime lambda mu nu a prime lambda, and we want this to be del x prime mu of xa times del x prime mu of xb times the original components dA ab, which are del A ab minus gamma c ab ac. Now, we have already figured out what del mu nu in the transformed coordinates are like. This is a piece which would be like the 0 to tensor. You have this tensorial property destroying term here. We do not know how gamma prime lambda mu nu transforms as of now. We want to figure that out. Of course, we know how a prime lambda is related to the old components. So we plug everything in. One good thing is we can get rid of this term and this term here, of course, after multiplication by this. So what you can guess or can figure out is gamma prime lambda mu nu del x c del x prime lambda ac. This term is going to be this plus this times this, which I have brought to the other side. We are almost there. All we need to do is rewrite this whole expression so that only the gamma prime is sitting on the left hand side. So we have to get rid of del x c del x prime lambda, also of the component AC. Let's tackle this component AC first. Remember, this expression has to be correct for all covectors. So as long as we have the same component for the covector on both sides, we can just say that the coefficients are going to be equal. The only problem is, on the right hand side here, you have AC and AB. Now that, of course, is a bit of a trouble. So what we do is we just relabel those dummy indices. Note that both the C's here, and the B's here are all dummy indices. Let's call them something else. Let's call them all D. So this becomes del x d del x prime lambda AD. Here also you have gamma D AB AD, and this becomes del 2 xd AD. So now we know that AD times this expression is essentially AD times this plus this for all AD, and that automatically tells us that the coefficients have to match on both sides. So we are left with this expression. Gamma prime lambda mu nu del x d del x prime lambda equals del x a del x prime mu del x b del x prime nu gamma d ab plus del 2 xd del x prime mu del x prime nu. The next step would be trying to get rid of this. And once again, all we have to do is multiply by the appropriate partial derivative and sum up. But the summing up is where we have to be careful. Lambda is already spoken for here. It's a dummy index. D is a free index. So what we need to do is multiply this by del xd of something. So what we do is multiply both sides by del xd of x prime rho. We do it on both sides. And here, of course, when you combine these together and sum up over d, you get delta of rho lambda. And this is exactly what you end up with. Gamma prime rho mu nu, the lambda becomes rho because of this delta symbol, is del x a del x prime mu del x b del x prime nu times del x prime rho del x d gamma d ab plus this piece del 2 xd del x prime mu del x prime nu del x prime rho del xd. So this is how these gamma lambda mu nu terms transform. Well, we can of course rewrite this with lambda mu nu here. All we have to remember is rewrite these rows here as lambdas, and what we have also done is change this d, which is dummy index anyway, to a. It was not necessary, but it just makes it look neater to use a smaller number of indices. Now, if you had just this one term, then this would have been a tensorial object, a 1, 2 tensor, as the position of the indices seem to suggest. However, as we have already argued, if the gammas were tensorial, then d, or rather d mu nu, would not have been. The additional piece that you have here ensures that the extra term that you get when a partial derivative transforms is cancelled out, and you end up with an actual tensorial transformation rule. Now, once again, let me also emphasize that because of the presence of this term, even if all the gammas were to vanish in one coordinate system, they may not vanish in a different coordinate system. That, of course, is a sign of the fact that they are not tensorial. Now, what are these things called? They are called connection coefficients. This is a set of d-cube coefficient functions gamma lambda mu nu, which you can define in one coordinate system and then demand that when you change the coordinate system to something else, it has to transform in this particular manner. Once you do that, you have got a set of connection coefficients. And once you have defined connection coefficients, you can use it to define a covariant derivative, a derivative of a covector field which itself transforms like a tensorial object. At this stage, the gammas are somewhat arbitrary. The only thing that you are demanding right now is that they be defined in one coordinate system to have whatever value you want, but in the other coordinate systems, they would have to obey the corresponding transformation law that we have written down, a non-tensorial transformation law. Now, when we talk about particular geometric situations, like situations where you have a length defined and you want to understand this covariant derivative in terms of how to parallelly transport a vector from one place to another while keeping its length and, so to speak, direction the same and so on, then we will have to put in additional demands on the gamma, lambda, mu, nu functions. We will discuss those things in greater detail in later lectures. Bye for today.